Okay. Okay, I hope you thought of some really good questions. At this time, we're going to ask Brad Thomson to come forward and let's give him a hand.
Do we need the microphone? I think you can all hear me without. Okay. Just a couple words of preamble. So I'm here at UT. Prior to UT, I came from Boston University, where I was there for a number of years. And before that, I worked at the Applied Physics Lab in Maryland. Before that, I worked at JPL. And I was actually thinking back, preparing for this this opportunity to dialogue with you, that Bruce Banner, he was on the floor I worked at JPL. So I was at JPL from 2006, 2008, and Bruce Banner, for those of you that are comic book fans, Bruce Banner is the name of the Incredible Hulk. Dr. Bruce Banner, this Dr. Bruce Banner. I never asked him how he felt about that joke, because I imagine he heard it a lot growing up and didn't hear it anymore. But he's a very mild-mannered person. I never saw him mad, never came agree with him. But he had this old, so back 2006, right? So 13 years ago, he had this old poster on his door, upside down, from the Netlander mission, which was a mission that went through a number of iterations. It was a joint ESA-NASA mission that was proposed in the late 1990s to send a network of seismometers. So most of the time when we send seismometers, we send, as Bruce mentioned, we send a bunch of them. And budget stuff happened, it got canceled. And so he's been trying to do some version of this mission for, like he said, his entire professional career. So, it's been at least 25 years in the making. We had seismometers on the Apollo missions. They worked pretty well, except for the one that the astronaut kicked the cable. They deployed it and kicked the cable out, so that one didn't work. But the rest of them worked fine, operated for a number of years. There were seismometers on the Viking missions to Mars, which landed in 1976. And those did not work so well, and we can talk about why those didn't work so well. Anyways, so I do mostly surface geology. I'm interested in the rates of surface change, so I study ancient river systems on Mars, ancient impact craters. I have taken seismology, but I will not be using the data that this spacecraft returns directly, but like I said, I'm a big fan of Bruce, and I'm very excited to see this mission finally get there. It was delayed from 2016 to 2018. It finally launched last May and arrived in November, and they had their first scientific presentations. We're at a meeting in March in Houston that I attended. It was a packed session. They had the fire marshal was outside saying people couldn't do it anymore. But it's very exciting, and they've only just begun. They only heard their first Mars quake this past week. Last week, I think, which is pretty exciting. So I have some slides that I could bring up and answer your questions, but this is not me talking, right? This is a dialogue. So fire away with your questions.
There are no tectonic plates on Mars, is that correct?
There are no tectonic plates, right? So yeah, so Mars, unlike Earth, right, the big difference is we call Mars, like the Moon, it's a one-plate planet. So it just has a single plate. So there still is tectonism, so that the sources of seismic data that this will be looking at, one will be impacts. We know that impacts hit the surface, and each of those imparts energy in the surface, and the seismometer is sensitive enough to pick them up. And there's also internal sources of energy as well. But yes, there's no tectonic plates now, so it's a one-plate planet now. Yes, sir?
Has anyone discovered if water is currently on Mars?
Has anyone discovered if water is currently on Mars? Actually, yes, there are hints. In particular, well, so we know that there are, you can look through a telescope at Mars, right? And it's got a bright part near the pole. So we know that there is frozen volatiles, CO2 mostly, but also water ice, that form at each winter pole. But if you're talking about liquid water, there's some evidence of small seeps. So the edge of steep areas, some of the high-powered cameras that have gone over have seen little trickles of things that could be salty water. But it's still a little bit of mystery. Like, is it just is it the type of stuff that forms on your lawn in the morning, right? Just sort of atmospheric dew, or is it actually tapping a deeper source of a deeper aquifer? And there's still a lot of debate about what exactly the source of some of these little seeps are. But they're considered special regions, so NASA, if we find one, we can't actually go touch it because it could have Martians living below that. So we haven't figured out yet how we're going to interrogate those particular seeps.
You know what the parameters were for selecting this landing site?
Yes, that's a good question, right? So where did they go? I think that was one of the first slides I had here.
I sent the wireless mouse over. There we go.
Okay, so where is InSight? So this is a global map of the topography of Mars, showing the names of some of the places we've landed, and then we just concluded, NASA, just concluded a selection for the Mars 2020 landing site, and that's going to go here, Jezero crater. But the InSight will be landing in, oops. Oh, let's go back. Oh, I can do it. I included an animation. There was supposed to be a star, but anyway. So we landed right here in Elysium Planitia. So this is Elysium Mons here. So it's the second largest volcanic cluster. You've got the Tharsis Montes here. This is Olympus Mons, the biggest volcano in the solar system. This is a smaller secondary volcanic center, and you can see the sort of low-lying terrain here. InSight is about right there, and it's. I have a couple pictures we can look at the landing site. It's just sort of a broad, flat plain. They picked it because it is just a safe place to land. Right? There wasn't a lot of steep slopes that you have to worry about, so they wanted to go to some place that was safe to land, and it's also low. So one of the reasons that InSight was selected. Oh,
Sorry, can you use the microphone? I think we're having a few people that have some trouble hearing.
Sorry, I talk fast, so I should make a point to slow down and talk about it.
And let me get you untangled there.
Yeah. So, unlike the most recent mission, so Mars 2020, that was an open public competition, really. So scientists from all over the world could propose places to go, and they had a series of meetings to argue about it. Because this was a PI-led mission, InSight was, the InSight team got to decide themselves where to go. And they mostly picked it, they wanted to go someplace low, because even though the spacecraft uses rockets to descend, earlier on it uses this hypersonic parachute, and it needs a certain thickness of atmosphere to really work well. So you couldn't land, for example, on this high terrain here. So this is elevation where red is high and blue is low. And so they had to target some of these blue areas, and it's also near the equator because this is a solar powered mission, right? So if you're up near the poles, you have less sunlight, it's colder, it's harder to operate. And the twin of this spacecraft, so that the same landing platform landed up there where that dot says Phoenix, and that was to explore. There's a subsurface ice layer that instrument used the same design of arm to scrape and retrieve some of that subsurface water.
Brings some follow-up questions.
Yeah.
With this environment, you expect to have volcanic ejector or flows from that volcano on the surface?
Correct.
Landing site?
Yeah, so the thought is that these are, they're ancient by terrestrial standards, I think a couple 100 million years, but pretty young by Martian standards. So the moon, for example, most of the surface is 3 billion years old. Mars is a bit younger, it still has, we think, recently active volcanism, recent in geologic timescales, not our human life scales. But yeah, so the thought is this is an ancient lava plain that's been beat up by subsequent impacts, but it's, and there should be, what the team was hoping for is a regolith, a rubbly layer on top that the mole could drill down through, and it did have some problems with that. Yes?
So do we understand correctly that there is sufficient atmosphere in some places to support the dropping of a parachute? Is that what you're saying?
Yeah. So Mars
How can we relatively relate that to something we may be familiar with here on Earth?
That's a good question. So Mars's atmosphere is about 1/100th the thickness of our atmosphere. So it's pretty thin. You know, if you recall the movie, what was that bad movie with Arnold Schwarzenegger, where he went to Mars and he at one point he was outside without a spacesuit.
Total Recall.
Total Recall, yeah, that's it. So you would asphyxiate pretty quickly if you were on the surface. It would be unpleasant. But there is a thin atmosphere. It's thick enough to move. The wind does move dust around and sand. And the cool thing about Mars, this is just a map of topography, but the way the atmosphere is thin enough that 1/4 of the atmosphere freezes out in whatever pole is winter. So if you watch Mars with a telescope, you'll see that first the southern pole will expand and then contract, and the northern one will in the opposite sense. So whatever pole is in winter, 1/4 to 1/3 of the atmosphere freezes out on that pole. Yes, ma'am.
Are any other countries interested in Mars?
Oh, yes. Are any other countries interested in Mars? Yeah. It's, so let's see. The Russians have had a long history of launching missions to Mars. And they have contributed instruments. ESA most recently attempted to land the Beagle lander. That was unsuccessful. That was in 2009, I think. The first Middle Eastern country, the United Arab Emirates, is launching a Mars mission soon to study the upper atmosphere of Mars. And then India is also launching Chandrayaan-2, I think, is going to Mars. So it's harder to get to, much harder to get to the moon, right? The moon is close. The moon, if you're a person who wants to travel to the moon, it's only 3 days away, right? Mars takes you 6 months to get there, you have to stay on the surface for a year, and then 6 months back. So it's just a much more challenging target to get to. So most other countries have focused on the moon just because it's easier to get to. But yes, people are interested in, other countries are interested in Mars as well.
Is it for defensive reasons?
It's mostly for prestige. You could make the case that the moon, there are resources there. You could, so we know that unlike the Earth, right? So the Earth is inclined and we have seasons. The moon and, well, Mars has an obliquity. The moon is pretty much straight up and down, and it means that there's regions near the north and south pole of the moon where the sun never shines, and they're very, very cold. And over geologic timescales, they've collected ice, they've collected volatile deposits. So there is this reservoir of stuff you could make rocket fuel from. We can use water to make fuel for rockets, we could use it for human consumption. And it's up there on the moon's surface in 1/6 Earth gravity. So it's very expensive, it's like $10,000 a pound to launch anything out of the Earth's gravity well. So the fact that there's this reservoir of materials on the moon means that there's more of an economic argument for going there than going to Mars. I mean, Mars, the argument is more, first of all, exploration. We like to explore places we haven't been before, and then also long-term survival of the species, right? At some point, we're going to hit with a really big impact. It's going to do a lot of damage. And really, we can try to deflect these things, of course, but one of the better long-term strategies is to be more than a one-planet species. So expanding to the moon, expanding to Mars is in the one. Plus, it's good to have psychologically, right? We're in America, we're lucky. This has always been some place where you can be like, dang with it, I'm gonna move where there's no people. You can't do that anymore. You can't be like, well, this place sucks, I'm gonna go somewhere else. We're running out of room, right? So there's certainly a psychological case that it's important to have terra incognito. You can just, if you're tired of where you're living, just pull up your stakes and go somewhere else. So probably the moon first and Mars a little bit further on, but yeah, it's definitely an exciting place to go. Yeah.
Has anybody, have they determined what surface rocks are there, specifically limestone?
Yeah, so do you mean at the inside landing itself, or just at Mars in general?
Mars in general, and I'm leading up to, are there caves on Mars?
So that's a good question, right? So there's Minnesota's the land of 10,000 lakes. Tennessee's the land of 10,000 caves, right? So there is not evidence, there is evidence for carbonates on Mars, which limestone, is CaCO3. And there is evidence for caves, but they appear to be mostly volcanic caves. So I got an email from a colleague, UT, Annette Engel, thank you, yeah, who is an expert in caves, who's going to speak to this group sometime later this summer. And the short answer is there's no limestone, but we do think that there are some caves in these volcanic tubes, and they are good places to shelter, certainly because they provide a natural microenvironment. But they're not, like the ones on Earth, right, are formed from rainwater that percolates down and gets acidified by CO2 and dissolves out and moves on. So there's nothing quite analogous on Mars that we found yet. But yes, there are caves. And most of the rocks you'll see in this field here, so this is mostly basalt. So if you've been to Hawaii, right, so Hawaii, it's a very dark rock, a lot of iron in it, and that is mostly Mars. And Mars is red for the same reason that, good Tennessee soil, right? You dig down and it is this bright red, and that's from oxidized iron in the soil, and Mars is covered with the very same thing. So this little GIF, by the way, this is the deployment of the SICE, the seismometer, instrument there on the surface. Yeah.
My wife had a question, but I'll ask it for her. Regarding the probe, the heat probe.
Yeah.
It's driven down mechanically, as we understand. And we all know that things that move through other surfaces generate by friction heat.
Yes.
This is a heat probe. How do you account for the heat generated by penetrating the probe? Because that's going to be the standard for extrapolating deeper, right?
Right. No, that's an excellent question, right? So it will generate some heat. If it was a rotary drill, it would generate a lot of heat, right? And that would be a big problem. So this thing has a linear actuator, so it's got a small impulse motor that drives it down like a millimeter or so at a time. And it will heat up, but the type of heat, and then it'll cool off is the answer. So it doesn't heat up enough to melt the rock, for example. It might heat it up a little bit as it moves down. But then the idea is once it's deployed to its full 5 meters depth, which is never going to happen because it hit a rock, over time, and by over time I mean, over a few days, it would cool enough where then you could just measure the natural background heat flow of Mars.
What is the probe made of?
Sorry?
Oh, that's a good question. What is the probe made of?
What is the probe made of? I think it's mostly tungsten. Well, the business end of it, I think, is tungsten carbide. So the same thing we use in drill bits in the earth. It's hard, it doesn't rust, and it's easier to machine than if it was made out of diamonds or something goofy like that. But so the problem is, those of you, how many folks here have gone camping at some point, right?
Just roughly.
Good. Now if you go camping, if it's a windy day, right, you got to pound your tent stakes in, and how many times you hit a rock pounding your tent stake? It seems like every time, right? There's always a rock right underneath where you pitch your tent. So this instrument unfortunately ran into the same problem in that you can see the surface here looks pretty good. Like the predictions from orbit were pretty good. There's not many rocks in the immediate vicinity of the working space of the rover, so they were hopeful that they would not encounter a rock. But they found one. I think this thing's only penetrated like 13 centimeters or something like that. And it's designed to go, 5 meters. And unfortunately, they don't, to my understanding, it was not designed to back up and move and start over. Which is, these things have limited budgets and
It's not a mobile lander, so it couldn't really move much of anywhere.
yeah, I mean, I think that, in theory, it could pull it out of its hole and put it somewhere else. But then the risk is, all right, well, this cable is pretty thin and fragile, so you don't want to yank the cable out. And it was designed to start from this bit being in this positioner, and if you just yanked it out of its hole, then I'm not sure that it could, I'm not sure how you would start it if it was just sitting, dangling on the surface. So I have not heard that they have any plans to retrieve it and move it. I think they just might leave it in place and call it a wash, which is unfortunate, but the seismometer was the principal focus of this mission.
So what do they think they're going to learn, given the fact that the big machine has failed?
Yeah, so if you look at a temperature profile of the surface, so if you're right at the surface, you experience big temperature swings, right? You heat up during the day, you cool off at night, and that decays with the amplitude as you go down to depth, which is why they wanted to go deep, because they're really interested in what is the temperature irrespective of these diurnal and seasonal fluctuations. So you could still try to answer that question, but you're limited because you don't really know. You've got this big amplitude variation. You don't know what it's dying down to. So I think they can do some characterization of the thermal inertia and thermal physical properties of the uppermost, 10 centimeters or something like that. But in terms of getting what's the heat flow from Mars, that's going to be really hard to answer. And that's exploration. Sometimes it works, sometimes it doesn't. Yes.
Did you point out that another site, I think it was the Phoenix site, that they also had a heat probe?
Yes, so Phoenix had it had a colleague, the gal who I shared an office with at JPL. She was involved in, let's see, so let's leave this one down here. So this is a refly of, that's kind of dark. This mission is a refly of the Phoenix mission, as I mentioned. It uses the same arm, more or less, but that arm, there we go. So this is putting the little windshield on top of the seismometer. The arm on Phoenix had a scoop and a rasp and three, they look like little, it looked like a fork, it had three little tines, and it was called Mecca. And so what it did is it was a thermal, it was electrical conductivity probe that it just put down in the soil and then ran a voltage through each of those tines. They had different resistivities.
So looking for volatiles or post-volatiles.
Yeah, mostly just to characterize, in part that just to characterize what's the relative humidity in the soil, I think was the principal objective of that instrument.
But that was the site that also thought to have ice, subsurface ice.
Yeah, so unlike Phoenix, so Phoenix is near the equator, so it's too warm to have ground ice. Phoenix, as you saw in that image, is way up north, and they did find it, right? So the issue there is, it always takes time to learn how to use a spacecraft. You build these spacecraft and you send it to some environment, and you kind of learn by doing how to operate it best. And with Phoenix, they were learning, they could scrape ice and they had trouble getting chunks of it out, and then it would sublimate pretty quick. And so they were really going through this slow process of learning how to use it, and then the problem with Phoenix is they only had 3 months to operate because they were going to lose the light. It was going to go in darkness and solar powered mission, so once the sun goes down, they were done. So they had, NASA came in half of the mission, said, you got to stop everything you're doing. You just got to grab up some of this stuff and dump it on the, they had a wet chemical oven. They were going to dump this soil and ice mixture and try to analyze it. So they had to short circuit the normal process of exploration, just grab and scoop and dump. And it mostly worked, but it was a bit more hurried than they would have liked to have done.
So would subsurface ice affect this type of heat probe?
This measurement would, yeah, but luckily there's no evidence of ice here. This is too close to the equator for there to be ground ice. Question in the back, yes?
Yeah, I'm kind of a money man myself, it costs lots of money to go there and lots of money to get back.
Yes.
Who is funding this? Is the taxpayer or what?
Yeah, so this is part of something called the Discovery Program. So NASA has 3 flavors of missions. They've got Discovery, New Frontiers, and Flagships. And this is the idea with Discovery is it's relatively small amounts of money. It was capped at $450 million, which sounds like a lot compared to Flagships, which are $1 billion plus. But if you notice the instrumentation here, so this is a French spectrometer, and the mole, which is trying to dig down and measure heat flow, is a German contribution instrument. So those are, they're for free in terms of, ESA has developed these instruments independently of NASA and given them to NASA to go fly to Mars. But of course, there's still engineering you can do to make it, talk to the spacecraft and run it and stuff like that. So they're free, but they're not really free. And it is often the case that on other, particularly ESA, so ESA stands for European Space Agency, and it's a consortium of all the countries in Europe. They get together and fly missions, and they'll often put out a call saying, okay, well, we're going to Venus, or we're going to wherever, and we'll accept US contributions, and we do the reverse. We say, okay, we're going to Mars, what instruments do you folks have on the shelves we could take and fly to Mars? And it's cheaper for us. But then there was a big cost delay, a cost upward trajectory with this particular mission because it was delayed from 2016 to 2018 launch, right? The launch window to Mars is every 2 years, and this seismometer is cool because it's encased in this little windshield here. Let's see, I think the next one is the cutaway view. It's actually got 2 shells, so this is to protect it from the wind, and this is supposed to be in vacuum, and it was leaking, and they couldn't figure out why. So they have these design reviews where you have to, it's like an internal, it's a review of all the components of the mission, and it failed its critical design review because it was leaking. So they couldn't launch it, and they ended up, it went from $600 million to $800 million. So, I mean, these missions get expensive, and, I'm very glad that it went and it's successful, but, at some point you gotta wonder, like, okay, well, if there's design problems, at what point do you say, no, you guys don't get any more money because, you mess things up? That's a question that's above my pay grade, but it does have to be a question. So there's a NASA designing a mission, for Europa currently, and there's a small magnetometer that has had all sorts of design problems, and they actually got their budget, they got cut off from the spacecraft. They said, okay, we're not putting this on the spacecraft anymore because of cost overruns. It was not a popular decision, but, you know, at some point, the person with a checkbook has to be like, no more checks for you, so. It's a good question. Yeah.
Back to the heat probe, couldn't something akin to ground penetrating radar be used for that short a depth to make sure that the site chosen had no rocks in it?
Yeah, let's see, so if, from orbit, it'd be we do have we do have penetrating radar from orbit, but they, the footprints are hundreds of meters to kilometers, so it wouldn't resolve small
I was
scale
thinking
rocks.
of something small that could come down onto the surface.
You know, if you could have surveyed the area, or even the local area with the GPR, then that would have been beneficial to help you pick where you're going to drill. The problem is that would, you know, add another instrument, and that would add cost to the mission. So this
Yeah,
is
but
a
the
very
probability of hitting a rock is pretty high.
right. I would agree. I was not involved in the design of this mission, and I would have been concerned. That is my concern as well. Yes, sir.
Actually, while we're on the topic of money, the mantra of NASA about 10 years ago, maybe 20 years ago now, was cheaper, smaller, faster, more, and like the Pathfinder mission was
Yeah.
one of the cheapest NASA missions ever. I think my recollection is it had fewer zeros than the number you gave. I wanted to say it was like something tiny. Like
It was less than 200 million. Yeah, this is
I was thinking it
1997.
was actually 20 million with
No,
one
no.
less zero, less than that. Okay.
Well, so I mean, sorry, what was your question about that?
Well, I mean, basically, is NASA still operating under that same mantra, or is that relegated to the past?
And that's another good question, yes. Pathfinder and NEAR was a mission to an asteroid. Those were the first discovery, that faster, better, cheaper program became the Discovery program. So it's a very vibrant program. They're supposed to compete it every 2 years, and there's anywhere between 15 and 30, or sometimes even more, individual mission ideas that'll be proposed, and NASA will down select and pick 2 or 3, and then down select again and pick some small number, 1 or 2. So this is that smaller category of mission. Now, interestingly, I worked on Chandrayaan-1, which was the first Indian orbiter of the moon, and the U.S. had an instrument on there. It was a radar on there, and that was a relatively inexpensive mission. The numbers, it never got a real good answer on what the total cost was, but they had a number. Their total cost of the mission, I think they claimed less than $100 million. So, and part of that is because of, salaries, right? So people make different salaries in different parts of the world, and if you outsource your engineering to a country where the wage is lower, then that's going to cost less. But part of it is also testing, right? So one of the fun things I did when I was at JPL is they have a JPL summer school. So those of you that are students, you can apply to go to JPL summer school, and you spend part of your summer out in California designing a mission. You get to learn all the component parts that help put it together. And one of the cool things that we did a mission to one of the outer gas giants, which as a geologist I don't care too much about because it doesn't have a solid surface, but it was good to learn about the process. And what I learned was the material components, like the amount you'd spend on the actual spacecraft, like hardware, nuts and bolts and cables, is like a few percent of the total budget, right? How can that be? And the reason is because, two reasons. You need to pay smart engineers to put these things together, and you also have to pay those same smart engineers to test the heck out of it. So our mission to the outer planets, it had this long cruise stage, and then it had to wake up. And so, we need a timer to wake it up, to say, we need to be asleep for 6 years and then wake up. And the timer, it's like a kitchen timer, right? It costs, $3, $4. Well, the whole mission, $100 million, several $100 million is going to depend on this $2 kitchen timer. Well, that's not good enough, right? So if you're an engineer, that gives you pause. So you say, we need redundancy, so we need 3 timers, and we need polling, and we need software that'll check each one. So if one has an aberration or goes off, it's not going to wake up too early and then go kaput. So, and then you have to take that timer and you have to put it in thermal vac tests. You gotta take it up to experience the range of temperatures that we experience in space. You have to shake it, do vibration tests. And at the end of the day, this $2 kitchen timer will cost you several $1 million to get on your spacecraft. Because, again, you have to engineer it and then test it to make sure that it's gonna work. So when you look at some other countries, Japan has launched a number of missions. They have tiny budgets, and India as well. Where you can shortcut is the testing, and then you have to deal with more failures. So, our missions tend to be pretty successful on the whole, and we see more successes than failures, and that's because we spend the money to test the living heck out of them. Yes.
Is there enough space stations and individual pieces of hardware that can be incorporated into different spacecraft, so you don't have to sort of reinvent the wheel again and use that same piece of gear
That's-
your timer?
That's the argument, yeah. I mean, so NASA has something called technology readiness levels. And so anything, technology, TRL for short, we love our NASA acronyms in NASA. TRL1 is just an idea, right? So if you write something down on a cocktail napkin, that's TRL1. If it's flown in a relative environment, then it's TRL9. So the argument for this mission was, well, we're reusing the spacecraft landing system was TRL9, the arm was TRL9. This thing was designed to fly, it was pretty high TRL because it was designed for a European mission that we pulled out of in 2012 called ExoMars, that is now going in 2020. So the US pulled out its mission and the Europeans said, all right, fine, we'll let the Russians do it. So now the Russians are launching that rocket instead of us. But the idea is that if you have hardware that has been to space, then it is deemed more reliable than just sort of off-the-shelf stuff you don't necessarily know about. So there definitely is a push to, and part of the reason the JPL is so good at this is because they have all this heritage, and they try to reuse as much as possible. Yeah.
What is the length of a day?
Length of a day on Mars. It's Martian Sol. It's 24 hours and 37 minutes. So that would really be nice. Would have taken an extra 37-minute nap. Really, just after lunch. It'd be nice to be on Mars time, I think. So it's pretty close to Earth. Yeah. Oh, sorry. Wait, before we get to this, you have not asked questions. Sir.
What are the average temperatures on Mars?
What are the average temperatures on Mars? They are cold. So the warmest it gets on Mars is just barely above freezing, and the average temperature is about 100 degrees. What is it? 100 degrees colder than zero. So minus 100 C is typical. So it's pretty dang cold. But the temperature range you would experience, interestingly enough, on the surface is less than the moon, right? Because the moon, it's locked with the Earth, and if you're in full sunlight, it's pretty warm. The astronauts had water-cooled undergarments, but then it freezes hard every night. So it's like a 200-degree thermal swing. Mars, because the days are more and more like ours, and it has an atmosphere, the range of temperatures is lower than the moon. Yes, sir.
Does the penetrating probe for the heat flow measurement, does it have any feedback on the how much progress it's making, or the resistance it's achieving? I'm thinking about figuring out how much is this a surface dust before you get into some other regular material.
Yeah. So it knows it has a counter for how many little impulses it delivers. And there's also this sort of, in the body of this thing here, you can see this cable kind of winding around. There's a counter on how much cable has wound out, which is also an indication of depth. And it's stalled out at this really shallow depth, and it's hammered like 20,000 times and made no more millimeters of progress. So I don't think it's going anywhere other than where it is now. And then there's also, this is instrumented with passive thermal sensors, and this also has additional heat sensors on the way down. So they can get some measurements of this uppermost surface layer, but yeah, just not that much. Yes, sir.
Yeah. Earlier you talked two benefits of exploring Mars.
Yeah.
One is our settlement, and other is using of resources.
Mm-hmm.
So if we find that there are resources that are beneficial to us, and if we import that to Earth, will that affect in our existence in terms of Earth's motion in any way?
Yeah,
because that's not our Earth material. That's a different material.
Right. So it would be hard to make an economic case to bring back ordinary materials from Mars. So if you found there's lots of iron in the rocks, it would not make a strong economic case to bring it back to Earth. It's more useful where it is.
Okay.
But there are very serious companies who are interested in asteroid mining. So there's some asteroids out there that there's a class of asteroids called M, which stands for metal, So they're giant hunks of platinum group asteroids with platinum group elements out there. So platinum, vanadium, rhenium, and the first person who takes one of these metal asteroids and brings it back to Earth is going to be a new King Midas, because it will be more than all of the materials that we have easily accessible on the Earth.
Now, will that affect our Earth's motion or weight of the Earth or in any way?
I mean, that's a good question, and I think they would probably, well, you wouldn't want to just crash it, right, because then they would just go everywhere. So you'd probably have to do a series of small missions to bring it back in pieces. Even the plans to mine asteroids, they're still relatively small. They're still, a few miles, 1.6 kilometers per mile, so under 10 kilometers in any longest dimension. It would still be small enough that it wouldn't do much to our orbit or anything like that. But the question of how would the world's economy be affected by dragging a metal-rich asteroid and mining it near space it will happen. It won't happen in our lifetime, but it will happen. Probably.
But one thing, what I say is, that's why you talk about the temperature of Mars and then temperature of Earth. Now, if I find something on Mars and if we are economically able to bring it over here, will that still be usable because of the difference in temperature?
Yeah, I mean, it's rocks are pretty insensitive to small changes in temperature, right? So, for example, there was a big fire, a very tragic fire in Brazil. Their national museum burned down. But as a geologist, I was very glad to learn that all the rocks were fine. Right? Because the rocks don't care about fire. All the artwork is, not doing so good, but the rocks are good. So it depends on what that material is, right? And but most of the geologic samples are pretty robust against small changes in temperature. Yeah. Yeah.
How accurate are the landing zones? Do you have like a 20-mile circle to shoot at?
Yeah, they have gotten better and better and better. So the place where NASA landed in 2012 in Gale Crater, that was proposed 10 years previously for the MERV, Mars Exploration Rover, but the landing of this was too big. Because it shrunk from like 160 kilometers to 80 kilometers, and now it's about a circle of about 20 kilometers. And part of the reason it's getting so small is that when the missions come down now, they've got a map of where they're going loaded in computer memory, and then it does something called terrain relative navigation. So it has radars that'll ping the surface on the way down and figure out exactly where it is, and it can move relative to the ground terrain. So one of the things, I haven't heard too much comment on this, but there's a descent video of China's U-2 lander, the one that landed on the far side of the moon. And that one did one of these, so the landing comes down like this, and you can see it kind of, just smoothly descending, and at some point it starts to move around like it's looking for terrain, and then it lands. So I'm not saying the Chinese have stolen that technology, but they have the same technology. It's very advanced NASA technology. I think it's one of the reasons that, as a NASA scientist, there's a prohibition against bilateral exchanges with China because of the worry about the leakage of this technology to China. So, but yes, there are radars that sense the local terrain and can make small adjustments to help steer away if there's known hazards, like maybe there's too rocky over there, or too slopes are too steep. So this thing is pretty cool. Has a leveling device, which luckily didn't have to use, but underneath this little guy, each of these, it's got 3 legs here, and you can kind of see there's a helical screw, so it can screw these up and down, so that this seismometer works best if it's level perfectly. And they did do some amount of leveling with the screws, but it could have withstood, I think, up to a 15-degree slope if it landed in a bad spot. But luckily, they didn't have to use it much. It was pretty level where they put it. Yeah.
With respect to the liquid solid core of Mars, how do you expect to learn what that is?
Yeah, so that's a good question. That gets to the central scientific game here. So this is my candy corn diagram here of Mars. So this is from this paper here in 2017, showing a cutaway view of the Earth on the right and Mars, what we think, on the left. So On the Earth, we've got, this tiny amount of crust, so that's an average crust. Obviously, the crust is, it's thicker on the continents and thinner in the ocean basins. You've got this big mantle core and then a solid inner core. And for Mars, we've got some crustal measurements. We can infer that from gravity. It's about half the diameter, roughly, of the Earth. And this is the big unknown, right? So the two questions are how big is the core? And it has a lot to do with how much sulfur is in the core. So we know that it's mostly iron and nickel, but there's some unknown amount of sulfur. And then we also don't know, does Mars have a small solid inner core or not? And so the way that we're going to tell that is, I pulled this complicated looking diagram out of here. Oops, let's go back one. So what this is supposed to show is some seismic event. This is a cutaway view of Mars, showing Mars with no inner core and Mars with an inner core. And the details, don't matter too much in terms of diagram, but you can see that depending on where you are relative to, so this would be a surface impact or a shallow seismic event that is strong enough to send signals. Depending on, you can see just on these ray tracing diagrams, depending on if there's an inner core or not, it has a pretty big effect on the propagation of these waves. So like in that video that was shown in the beginning, so it's the surface wave. The seismometer is sensitive enough. It's, I think it's about 1 million times more sensitive than the ones we flew in the Apollo program. And what we're looking for is the ringing of Mars. So not just the first passage. So you've got, when something happens, you want to be able to triangulate it. Normally you use network, but here we only have one node. So we want to detect the first passage of that seismic energy, the second passage, and the third passage loops all the way around Mars. It gets fainter as it goes. It loses energy as it travels through the crust. We can detect this ringing, and you can get a distance, and then if you know something about the polarity of the Rayleigh wave, you can get the azimuth, the direction as well. Yeah?
What did we find on the moon when we did seismic testing?
What did we find on the moon? So we found there was deep moonquakes. We saw so that it's, I'm trying to think if they had a good handle on the impact rate. I think the Apollo seismometers were a bit noisier. I mean, it was older technology, right? The technology is improved. So we were able to determine the core mantle boundary on the moon. It's the moon's core is pretty tiny, I actually didn't prepare any material for it, but we also get the inner core dimensions from precision tracking of the surface. We use an X-band tracker to look for small changes in the moon or Mars's motion, and there's a sloshing you can detect inner core is liquid. Sorry, so repeat your question again.
Well, was there anything unusual about the moon that they didn't expect?
Well, I mean, it was just unknown, right? How big is the core? I mean, so we knew that the moon and Mars both lack magnetic fields, so that's an indication that there isn't a big active dynamic core. But still, I mean, the diameter of the core is just a fundamental unknown. So determining that number was a big result for the moon, and it feeds into your thermal models for how you think the moon evolves and stuff like that. And on Mars, it's relevant because one of our unexpected findings was this magnetic signature that we found by accident in 1999. Before I go on about that, yes, ma'am, you have a question?
Yes, I was just wondering, what will studying Mars's geology tell us about the history of geology on Earth?
What will studying Mars's geology tell us about the history of geology on Earth? So a couple things, right? So the first answer is that we have a very good recycling system for surfaces on the Earth, right? So the ocean basins cover 70% of the Earth, and their average age is less than 200 million years old. Now that sounds old, but the Earth is 4.57 billion years old. So, in a football analogy, that's like, stripping away 95 yards, right? So on Mars and the Moon, that earlier record of activity is preserved. So one of the interesting things that we have learned from study of this ancient period of Mars and the Moon is that there was apparently a giant cataclysm in our solar system 3.7 billion years ago. And I could probably find it on the computer here, but there's there's something called the Nice model, which stands for, it's spelled nice, like Nice in France, and it has to do with the migration of the outer planets. And it turns out that the dynamical modeling informed by the samples from the Moon and Mars, we think we figured out that there was this outward migration of Jupiter and Saturn and Uranus and Neptune, and Uranus and Neptune actually switched places, which is pretty crazy to think about. Anyways, they destabilized something called the Kuiper belt, which is now further out, and it flung stuff all over the inner solar system. And that's why, if you look at the ages of the basins of the Moon, for example, there's like 45 basins clustered in just a very narrow time window, and we think it's because of this destabilization. So this is something that we really don't have any record of this in the Earth, right? So we don't really know too much about it, and it's only through studying the rock record where it exists, preserved from this earlier time, on places like Mars and the Moon, that we can figure out the details of this early period of our evolution. Yeah.
Wasn't there, like, I know we're jumping to Earth and we're talking about Mars, but microbiology, like, didn't that like spark up at that point in time on Earth?
Yes. So we keep finding, so the oldest rocks on the Earth are, they're actually, we have zircons, which are pretty hard to destroy once they form. So zircon, in sediments that are recycled pieces of older rocks. And the oldest evidence of bacteria and algal mats, those top out, it's 3 point something. So this is older still, but we don't, like I said, on the Earth we don't have a lot of rocks that record this early period. But once life starts, it's pretty hard to kill, it turns out, right? So it just keeps on living. At least bacteria and bugs are like, think of cockroaches, right? How hard it is, how much money we spend trying to kill cockroaches. And we're never going to get rid of them. They're going to be with us forever. Yes.
This may be very elementary, but I'd like to know.
Yes, ma'am.
When you drill, you drill from a cable. You've got a cable that is onto the probe.
Yeah.
When this probe is making vibrations, it compacts as it goes.
Probably, yeah, a little bit.
Okay, what I'm wondering is, as the sediment compacts around the cable, how does the probe pull it down?
That's a good question, and there's no rotary component to this particular mole. This just a linear actuator. It's as if someone was pounding the back of it a little bit at a time, tunk, 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 all the way down, and that it does. I couldn't tell you exactly how big the mass is in it that does this linear motion, but it's enough to drive it down a little bit with each little tap, and the cable has to be strong enough to withstand both that little bit of pulling and then the walls collapsing too.
I'm talking that it should squeeze the cable.
I don't know if it collapses entirely behind it. I mean, it's a pretty, the cable is, you can see in that diagram, it's not like a fishing line, right? It's actually a pretty wide cable. So I think it's able to maintain some tensional strength. And the Germans made this, and there's no doubt they over-engineered the heck out of that cable. It's good German engineering. Yeah, so you can see it's a ribbon, and if I was designing that cable, it would probably have Kevlar in it, right? So a very light material, like stuff you make bulletproof vests out of. It's very difficult to rip, so you can get crushed, but it's not unlikely to tear. Yeah.
Where's the actual actuator, the tip, or?
It's somewhere, yeah, I don't think I have a cutaway diagram, but inside this is like, I think it's roughly the size and shape of a tube in a paper
It's all self-contained.
towel. Yeah.
Okay.
And it's got a spring and this actuator, and it has sensors and everything in this one little, I think it's thinner than this thing, my understanding. It's a little bit longer. Yeah.
To understand my wife's question, you have to know that her background is in pile driving. So she's very familiar with driving to bearing when everything stops, because the friction around the tube being driven won't allow any more driving. So that's the basis of her question.
Yeah, I mean, it's a good, you know, we messed this up the first time we sent astronauts to the moon. So the astronauts had these, they had this drill, they had a tube with rotary helicals around the outside, and they drilled it into the thing and then attached a second tube to it, drilled it down. Well, the person who made that tube was not a geologist because they didn't make the flutes continuous along the outside of this thing. So you get one set of flutes and then a coupling, and it turns out that the cuttings, the rock that was, and this is on the moon now, the astronauts, the Apollo astronauts, they drilled down and the cuttings bound the drill string in the hole. And one of the astronauts had pretty close to a heart attack trying to pull this thing out of the ground. So they redesigned it for the next mission to make the flutes continuous so that the cuttings would be cleared from the hole. But I mean, this type of problem has already been a problem for the space program. We've already almost lost an astronaut to a heart attack on the moon trying to yank this thing out of the hole. I think it was Paul. Yeah.
Periodically, the Earth has a meteor shower.
Yeah.
Fairly regular. Presumably, Mars is getting hit by these same things
Yes, sir.
also, but they have no atmosphere, which
Right.
means greater impacts, I would presume.
Yeah, so-
What is happening to what extent is the Martian surface altered each time it passes through one of these clusters of junk?
Yeah, that's a great question. So if you look at the moon has no atmosphere, and so even sand grains will come in and impact the surface from space moving at cosmic velocities, and they'll make a little and that actually drives a lot of surface change. So the Apollo astronaut footprints are only going to last tens of thousands of years or less, because this churning of micrometeorites is going to overturn the surface layer in that sort
Or
of
if one
timescale.
big hit, they're gone.
Yeah, one big hit, they're gone, but I'm talking about just sort of small sand dust grains are enough to, over time, it's almost a continual rain of particles. Mars has a little bit of a filter, Earth has more of a filter, Venus has even a bigger filter. So Venus, the atmosphere is 100 times thicker than the Earth. So Venus, you have to be pretty big to get into the atmosphere of Venus. Mars screens or shields most impacts, we think, smaller than about 5 to 10 meters. There's a few smaller things that may have been larger impacts that came through and decelerated and made like a plot crater. So you screen out the smallest segment of the impacted population, but there's still plenty of things that are, now you need something the size of a baseball instead of a sand grain to get through. But there's lots of baseball-sized objects out there that come in and can do damage. So it'll be a hazard for when we send people, right? They're gonna have to build a hab that has some sort of protection against meteor showers and stuff, absolutely.
Can the meteor showers on Mars be observed from Earth? Or are they too minute relative to the distance?
That's a good question. I think the rovers have done some observational campaigns. So the MER rovers have cameras that that operate, and some of them are fisheye lenses. And I think they have seen some evidence of meteor showers on Mars. Now they're different than the ones, so Mars is its larger orbit means that it's not like Halley's Comet exactly that has a debris stream that Mars goes through. So, but they're different, the equivalent of Perseids and Leonids on Mars as there are for the Earth. They're probably regular occurrences of meteor showers, just like there are here. Yeah.
Are there any plans to put a satellite or drones or anything on Mars?
Yes. Drone definitely. So the Mars 2020 mission is going to have a helicopter scout. So it's going to have it's a little cube-sized. It's a little bit bigger than this microphone stand, and it has a double-bladed helicopter with 2 meter. I think they're about 2 meter long blades. Again, because the atmosphere is so thin. And the idea is this thing can fly it's solar powered. It can fly for about 25 minutes, I think is the estimate, and it has a camera on it. And so it's going to go take off from so the next big mission to Mars, we're talking about Curiosity, so this is one later in 2012. We're going to send another one of those in 2020, and it's just called the Mars 2020 mission until we come up with a better name for it. But it will have this small helicopter that the idea is it will scoot around in front of where the lander is going to go and take a bunch of pictures and help plan the path better. So it's not quite like a drone, but it's pretty close on Mars. And GoPro is the camera, and I think GoPro sponsors the helicopter. Why not? Helicopter on Mars. Yeah.
What's the leading hypothesis about the loss of Mars' atmosphere?
The leading hypothesis, the loss of Mars atmosphere. Another good question. So we think it's tied to this here. So right, so we're lucky here on Earth. We've got an ozone layer that protects from UV. We've got a magnetic field we live in that stands off the solar wind. So the solar wind is a stream of particles that's always streaming out from the sun. And if it was to interact directly with our atmosphere, over time it would abrade it. It would strip away oxygen and nitrogen and drive it off of our atmosphere. So Mars has this magnetic signature we measure that is remnant. So this is not due to currently active magnetic fields. This is only detectable. This is a remnant magnetic field that's trapped in the rock. So there was once, when these rocks cooled below the Curie temperature about 600 degrees when they first formed, they captured this magnetic signal, and then we don't see it in a lot of Mars. So it's kind of hard to see in this diagram, but this is an impact basin called Hellas, and you can see there's none of these red marks indicating high field strength measurements in here. So this basin is about 4 billion years old, and that says by the Martian dynamo had to have shut down by around about 4 billion years. And the reason is because simply of size, right? So, if you have a big pot of soup on the stove and you take a small cup from that, that small cup is going to cool way faster than the big pot. And it's because it just takes longer for that heat to diffuse away from the big thing. So same thing is true with planets. A planet like Mars is only half as big as the Earth, and so it cools much more rapidly because it is different surface area to volume ratio. And that means that the core circulation slowed down and then stopped at some point, and the dynamo, we think, ceased, and that meant that the solar wind could now directly mess with the Martian atmosphere, and over time it ablated it. And the fact that it's also lower mass means there's just less gravity to hold on to the components of the Martian atmosphere.
Who wrote the first paper about that hypothesis?
Oh, that's a good question. This was,
Is that a geophysicist?
well, this was discovered by accident because we aerobraked a broken solar panel on Mars Global Surveyor. We had to do more aerobraking than we wanted to initially. So these measurements, this was not a gold mission, but it did these deep dives in the Martian atmosphere. This was measurement 9. Most of the speculation about this atmospheric erosive process started after 1999. So I'm sure there were, if you go back into Harold Urey, Carl Sagan, there's probably some thinkers that may have considered this before, but the first time we got real data that speaks to this, what happened to Mars's atmosphere, is 1999. Not that long ago, 20 years. 30 years. Yeah. Oh, it's 20 years. 99. 99. Yeah. So I have a question for you guys. So I mentioned the Viking landers had seismometers on it. One of them didn't work. It didn't work right after they landed, but one of them, Viking 2, worked for at least a couple months. Took data for a couple months, but it was 100 to 1,000 times less sensitive than the seismometers that the Apollo astronauts took to the moon. So why do you think that was the case? So Apollo, it's same 60s era technology, right? So 60s, 70s, the moon ones put in place by the astronauts worked 1,000 times better than the ones that were on the Mars lander. Why do you think that?
The amount of iron ore or metal?
Yeah, that would. If it was a magnetometer, that could muck it up. But that's
Just the density, I'm thinking.
well, they're both basalts. They both landed on basalt. So there are chemical differences between basalts on the moon and basalts on Mars, definitely, but they're pretty minor.
Are you asking why it worked less well on Mars?
Yeah.
Even though it was the same technology?
Same technology, but it worked crappier on Mars. Why do you think that was the case?
It's the same type of instrument.
Basically, yeah. I mean, so all these seismometers, it's basically, it's digital now, but it's a spring, it's an inertial mass that stays in place. So the thing shakes and it measures the small shaking because it doesn't move because it's suspended in some way. It worked less well on Mars than the moon, even though it's the same technology. It's probably a little better because the one on Mars was a couple years later. Last mission was in 1972, the ones on Mars landed in 1976.
Did something happen in transit that affected it?
It could have, but that is not the answer. Yeah, it was a longer Yes, ma'am.
Maybe because the surface of Mars is much harder than the moon?
So surface conditions, yeah,
Temperature.
could have something to do with it, temperature.
I don't know what it is, but it has something to do with components that were used between the two of them.
Well, actually, it's something to do with the way they were installed.
Was it the human component?
Yeah, right, so the Apollo astronauts actually drilled a hole for their heat pump, but they actually put the seismometer on the surface, just like this one is here. But the Viking mission, it was on the deck of the lander. I don't think
Oh, so you got vibrations from the winds.
Yeah, it had vibrations from the wind, and then, you know, it just had all this noise they had to deal with, and it was just so much less sensitive because it wasn't on the surface, it was on, it'd be like putting on this chair, this table, right? You have a much more difficult chance of picking up those small vibrations. Right, but this one is right on the surface, so it'll pick up any little wiggle on the surface, whereas if you would put it on this table, then that would damp all the vibrations that it felt. So that's why, yeah.
I was curious about the sensitivity in relation to impactors. So I remember a couple of years ago, they purposely impacted a spacecraft on one of the poles of the moon.
Yep.
And that was to see if they could uncover some ice or something like that.
Exactly right.
So, small spacecraft relative to a large planet or planetoid, the moon, a seismometer like the one that's on Mars, would it have been able to pick up something as small as, you know, a man-made craft colliding in, or would it have to be a much larger mass that's hit it?
That's a good question, and the only reason I know the answer is because I looked it up before coming here.
Really?
The Apollo seismometer sensitivity was, they claimed it was sensitive enough, these are the ones the astronauts placed on the surface, right on the surface, that it would detect a 1 kilogram mass impactor anywhere on the moon. Okay. So 1 kilogram, you know, so sort of less than, you know, baseball size impactor. And the ones on Mars today are orders of magnitude more sensitive than those Apollo ones.
Okay, so that being the case, I know we didn't talk about it for this talk, but as the orbiter was approaching, it released a few extra craft that are now flying around Mars and checking the polar tilt or the tilt of the planet and all that. So, I mean, could they theoretically like aim those little suitcase-sized devices when they're done with them at strategic places on Mars, and then be able to pick that up, like to get a wave that might, you know, travel or be blocked?
That, you know, that would have been a great idea, right? So there is a history of using crashed hardware as seismic sources. So the Apollo seismometers picked up the upper stage of the Saturn 4B that launched them into lunar orbit. Those crashed on the moon at some point, and those were detected by the seismometers. The two spacecraft referred to, there were two small ride-along missions that were designed to do comms during descent, right? So descent, you're screaming through the atmosphere, you've got this plasma all around you, it's very difficult to have radio communications through this plasma, except in the, you know, right behind you. So there's a very small cone of potentially RF clear zone where you could transmit, and that's where these spacecraft were. I think it's lost contact with them because they didn't have much, you know, they were so small they didn't have much attitude control, you know, no fuel to direct them. And my read was, as of a couple weeks ago, they have lost contact with them. So they're out there tumbling uncontrolled. And I haven't seen a long-term projection of what their orbits are going to do. If they're going to be captured by Mars or just, you know, orbit the sun, what's one of those two. But yes, but if those hit, they would be big enough to detect with this seismometer. But the question is, when do they get hit? And I don't know the answer to that.
So 2020 and ever how often they would say, I mean, as long as this seismometer is in operation, I mean, they could potentially reuse pieces of future missions as projectiles for that.
Yeah, I mean, I think that they expect, I don't know if I've seen a clear prediction of how many impacts they expect to be able to record, but I think it's like 1 every 2 months at minimum. That'd be pretty big. And so that's that. I'm a collaborator on one of the camera instruments orbiting Mars, and we've done this campaign to look at recent impacts. So there's a camera which takes wide-angle views of Mars, and if it hits a dusty area, we see not the crater itself usually, but this big dust explosion from it, where it scoured dust away and disturbed the surface and made a little darker region. And we can go look at those regions again with a higher res camera and figure, okay, there's the hole it made, and we counted these. You know, okay, well, when was the first picture taken? When was the second one? When can we narrow down when these impacts occurred over time? And they occur with some regularity, so there should be a dozen a year.
Yeah, I mean, every impact would give us another data point, but perhaps I guess what I'm thinking is ideally, perhaps you would want to have the seismometer be, on the opposite side of the planet from the impactor, so you can see like a wave traveling through the center. Correct me if I'm wrong, but I would think there would be some strategic places that would give you more data than just a random event.
Yeah, I think they do a pretty good job with wherever it hits. I mean, I think the tricky bit is you need to measure these multiple, so you need, as Bruce mentioned in his video there, you need 3 passages of that wave to really nail down exactly where it is. And each time it passes, it gets weaker. So the bigger, you can probably have a first detection of some small impacts, but you won't know exactly, where they are on Mars. You really need this multiple passage of the seismic wave to really narrow that down, and that will only be true for the largest ones.
Yeah.
So there'll probably be a population of smaller ones that won't be able to figure out exactly where they came from. They need the biggest ones to sort it out.
Our time is getting short, so I think we ought to maybe ask 2 more questions, and then we'll have to close up.
You raise your hand up. Yes, ma'am.
Yes, so earlier you mentioned it's better to use something that has already got the space because it's more reliable, but there's also aging and it's also more use as opposed to something new altogether. So is there a metric on how many times you can keep sending it to space and it's going to be worse than a new one?
That is an excellent question, and that is a subject of active debate because the idea is that it's not necessarily the hardware that's been to space, but the design that has been to space. So one of the reasons that we use, if you look at the technical specifications for the computers on these, they are not impressive, right? Like this laptop is way more powerful than some of these. And it's because we're using older technology that we know has been proven to be hardened against radiation and thermal variations and stuff like that. So it's not so much we're using the exact same components, but we're using the same type of components that have shown reliability in space. But you're right, you wouldn't necessarily want to go and reuse something that's been gathering dust for 20 years or been to Mars and back. But that same type of rocket engine system or computer part, if it's been there before, then we'll know that it's probably going to survive. That's a good question. All right, who wants the last question? Last burning question. Yes.
Maybe beyond your field, but there was a story on Morning Edition the other day talking about the likelihood of asteroid impacts on Earth, maybe significant ones.
Yes.
And the need to map stuff. And that we've mapped like 0.1% or something like that of things potentially could hit us. Is the technology available to really do the mapping that we need at this point?
That is another good question. So impact hazards are a definite problem for the long-term survival of our species. No joke. I mean, the dinosaurs are not here because of one of these things. We think we know where most of the really ginormous, like the Chicxulub was the one impactor that hit the Yucatan Peninsula that had a big element of why the dinosaurs are died out. We think we have a good handle on that size impactor. But as you go smaller, it's a power law distribution, which means that you go down a factor of 10 in size, and there's a factor of 1,000 times that number of objects. So that means that, so if we're talking, that one was, like about 10 kilometers in diameter. If you go down to 1 kilometer, we know most of those. If you go down to 100 meters in diameter, which is still big enough to take out a city, or, France, those we do not have a good handle on. So, and it does take just observing time, yeah. So, and it's also, we're also rapidly running out of places to do this type of observing, right? Because there's more cities now. If you go to Arizona, right, they're very sensitive to the fact that there's, with all the astronomy things going on, we don't want light pollution. right? You know, so if you go out in the big city, you know, if you stand in the middle of Market Square and look up, you know, you can see just a few stars. If you drive a couple hours north of here, you can see the, you know, it's amazing what the difference you can see. And so you need dark sky conditions to make these types of observations, which we have on Mauna Kea and in Arizona and other places. But yeah, I mean, it's more just resources, you know, how much, like everything else, you know, every part of NASA has to justify its existence. So, you know, how much we want to spend on paying astronomers night after night to look at the sky and take pictures versus, you know, if we have to fund everything else, roads, bridges, everything else. There's the balance between all these things. So we're working on it from the biggest on down.
What about the orbiting telescopes that we have? Do they aid in this, or are they not designed for that?
I think they're mostly designed to, I mean, we've got a lot of ones coming down the pipe that are designed to look for exoplanets. So small, they're looking at individual stars and measuring the wiggle spectroscopically around them, or the actual occlusion if a planet comes between the star and us. Debris is, you know, it's not as exciting as a topic, right? I mean, it's hard to explain. I don't know.
Is there not a craft in orbit around the sun between the orbits of Mercury and Venus that is actually looking out in the solar system at the debris? I believe I saw a news article about this, but I'm not 100% sure if it was something that has already been launched or if it's going to launch very soon. Do you know anything about that?
No, I mean, there's been a couple surveys. The NEOWISE survey is one that comes to mind, that have done this type of thing where they take all sky images. I'm thinking from the ground. But if you're talking about a specific mission to characterize debris, you know, it would be a good idea. So. But again, you know, I'm mostly interested in things that have solid surfaces, right?
Yeah.
So, you know, the bigger the better. But the real answer is I don't know, but it would be a good idea. I mean, okay. And the best part is if you find one of these things, right, you get to name it. So, you know, and there's quite a cottage industry of goofy names for these things. So I think if you're going to do astronomy, you get the benefit of having some object in our solar system that you can name yourself, whatever you want to name it. So it's a good reason to conduct this type of research.
Bob.
Yeah, Bob. Ask for Bob.
Just hope it's not the big one.
Yeah.
All right. Well, before we go, let me just give you a quick rundown of the upcoming cafes. We've got the one next month. This is on June the 13th. This is we've got a stack of these little black and white flyers. And we've got some color ones. They're all in the back. Help us advertise, please, and take one. The speaker that is next month is Janice Whitehead. She is the president and CEO of Alzheimer's Foundation. If you know anybody that was last month, she was one of our co-presenters last month, and she's coming back to talk about Alzheimer's and diet. That's June 13 here. And then if you might be familiar with Stephen Lynn Bales. He's recently retired from Iowa's Nature Center. He's a naturalist, and also he's a science author. And he's going to be talking about summertime cicadas and tips for science authors. So with the broad spectrum, I actually expect that to be so very well attended. So we actually have scheduled that twice. One is going to be here, it's on July 11, and then the exact same topic, same speaker over at our last time for meeting at the Zoo Knoxville, July 22. So if you know anybody that's interested in that, of course, in the summertime, at that part of the year that you will hear all the cicada sounds in the afternoon and have all those good summertime feelings. Then August the 8th, that's the day that Annette Engel is going to be here for the talk on volcano. The topic is living volcanoes because she goes inside the lava tubes to study the creatures that live inside the lava tubes. That blows my mind. I think, okay, there was lava flowing here and now there's creatures living in it. I hope they let it cool down a little bit or whatever. But she was actually, she made a trip to Hawaii, and actually it was a camera crew from NOVA that recorded, and actually there's a program, an episode of NOVA about this topic. So So that'll be August the 8th here at Bearden Library. And then September the 19th, that'll be here at the library again. We have a returning speaker, Susan Garawecki. She is a geologist, got her PhD at University of South Carolina, but she works here locally in Knoxville. She was a speaker all the way back in 2012 on a topic of underwater caves in the Bahamas, but she's going to be talking about sinkholes. I was personally affected by a sinkhole 2 years ago. I had one open up in my front yard, and thankfully it wasn't the house-eating kind. It was just one of these little annoying things that took a while to deal with.
One across the street, by the way.
Oh yeah, the one over. There used to be a furniture store where Whole Foods is. Yeah, there was a large one that opened up there a couple of years ago. So yes. So anyways, that you may in Tennessee, who was it said earlier, with the land of 1,000 caves? Yeah, that's all over. So that is September the 19th, and then we just reserved some more meeting dates for the fall. One of our most highly attended topics was a lady that deals in forensics. She actually got her PhD at UT working at the body farm. We're trying to get her back for sometime closer to the holidays, Christmas holidays, so hopefully I'll have something to announce in a month or two about that. But if you know anyone that does research and would like to share, send them our way. We'd like to have them come and join us. Thank you all for coming. Don't forget, if you want to receive our announcements by email, write your name and email address down and drop it in the bucket. The little child that was here borrowed our pad of paper, so you'll have to come up with your own paper. So, but thank you all for coming. We'll see you next month.